Yes. Thank you, everyone. I would like to mention the names of my co-authors, Laouen and Dmitry. Dmitry is there, so anyone can talk to him as well about this. We are from the University of Copenhagen. So I would like to start by talking about the motivation behind this research. And the motivation is the following. We are working with something called stream processing, which is programs that can compute with possibly unbounded sequence of data, which we call streams. And there are a few frameworks that allow you to define more easily these kinds of programs, for example, Flink and timely data flow. But we are more interested in timely data flow in this research. So our research is about timely data flow. And our long-term goal is to mechanically verify timely data flow algorithms in a proof assistant. So soon enough, we realized, OK, we need a foundation to represent this kind of algorithm. And OK, we start our search for a foundation for that. And we found a good one. And this good one is non-deterministic asynchronous data flow. So I'll explain what this thing is. I'll start with data flow. Well, data flow is a direct graph of interconnected operators. And operators are just possibly non-terminating processes that communicate with the network. Network are just unbounded first in, first out queues. And asynchronous means that operators can execute independently, meaning that there's no orchestrator. And operators can also freely communicate with the network, do reads and writes, and they also can do silent computation steps. Non-deterministic means that the operators can make non-deterministic choices. So the non-deterministic thing here is the operators are non-deterministic, right? And the question is, OK, how do we know that something is non-deterministic asynchronous data flow? The answer for that question is provided by this paper called Network Algebra for Asynchronous Data Flow by Bextra et al. And in this paper, they present algebra for non-deterministic asynchronous data flow. This algebra contains a few primitives, for example, sequential and parallel composition, and also loops, and some other primitives that I'll mention later. And this algebra has 52 axioms about those primitives. And in this paper, they also provide the instance of this algebra using a process calculus. OK, so what are our contributions here? We provide a new instance of non-deterministic asynchronous data flow. We do that by defining operators as a shell embedding as code data types. And we prove 51 of the axioms. So I'll start by explaining the operators. So this is our code data type. And you see here we have 3 type parameters. I are the input ports, O are the output ports, and D is the data type, the data that the operators handle. And we have 4 constructors. I'll start with this first one here, is the read. So the read has as first argument the input port, and the second argument is a function that receives the data and returns the operator. The second constructor is the write. The write has as first argument an operator. The second argument is the output port, and D is the data that we are outputting. We have the sonic constructor that has a single constructor with an operator. And then we have the choice constructor that has a countable set represented by this C set here of operators. So one representation that you can see, for example, is this drawing here. We have an instance in which you have 2 input ports and 1 output. And we are, for example, manipulating natural numbers with this operator here. So a few more examples. We have a few uncommunicative operators. They all don't communicate with the network, but they do that in different ways. So the first one is just a choice constructor with an empty set. This little C here means that we're talking about countable sets, right? So it's an empty countable set here. The next example is just an operator that does a silent step and co-recurses immediately. And the last one is one that has one single element in the choice. That is the co-recursion. Well, they all are different operators, but they sort of behave the same, right? They are all incommunicative. We have a few more examples here. The first one is a choice that has 2 elements in the set, The first element is a write. So we write the number 42 at port 1, and then we co-recurse. The second element is one of the uncommunicative operators that we saw before. And then we have the next example here. We have a choice again. The first element is the same as before, but now the second element is a direct co-recursion. And this last example here is pretty similar than before, but now the co-recursion is guarded by a signed step. Again, all these three operators are different, but they behave the same. And now the thing is, well, they are different, but they behave the same, and you want to have some sort of equivalence relation that will show them to behave the same, basically. But also we would like that this equivalence relation to have a useful reasonable principle. And well, a pretty standard choice for that is to use Milner's approach, which is to use weak by similarity. So weak by similarity is a pretty standard equivalence relation of processes, and you can learn more about it reading this book here by Milner. So I'll explain very briefly. So it's based on label transition systems, and weak means that the sign computations are abstracted away. So of course, to define our weak by similarity for operators, we first define our labels of our label transition system. In this case, we have the read, the write, and the sign step, represented by the letter tau. And then weak by similarity of operators is basically the label transition system with a definition of weak simulation and a definition of greatest weak by simulation. And as expected, weak by similarity has a useful co-induction principle that you can use to prove things. And we can prove all the equivalence that we want to prove before. OK, now I can talk about the operators of the algebra. So, but before that, I need to mention a few auxiliary definitions. So the operators often have a state. They're stateful. And the state is a buffer. And the buffer is basically a function from a port to a list of data. And then we have three functions to manipulate the buffers. So the first one basically takes the head of a buffer at port P. The second one computes the tail of a buffer in a port P. And the last one enqueues element X at port P. Another useful function that we need is the choices function. And the choice function has this following type here. So it's a function that receives an operator and returns a countable set of operators. And a way of seeing this function is that in the set there will not have any choice constructor there. So in this set here, you only see read, write, and silent. And a last function to mention here is the mapping ports function, which will map the ports of operator. So we can, for example, map the inputs, map the outputs. So we get the operator here, and you get the mapped operator by the end. And two useful functions to give to map up are these two here that are basically reassociating the sum type. So they are reassociating both directions. OK, now I can start talking about one of the operators of the algebra. And the first one is the identity operator. So the identity operator, as you see here, has a buffer as argument and then returns an operator. And this operator is defined as a choice. And this choice has a set inside, as you remember. And this set is split in two parts. That's why we have a union here. The first part are the reads. So we have this set here, which is the set of usable parts that is provided by the type that we have instantiated the operator. And here I just basically define the reads. So you read from port R, and then you enqueue the element that you read, and then you co-recurse. And we have the second part of the operator, which are the writes of the operator. So here we need to be a bit careful because we are writing what we have stored in the buffer. Therefore, we need to filter out when a buffer is empty in a particular port. So we map over this set here, and then we define the writes by basically writing out the element at the head at the buffer port P, and then computing the tail before co-recursing. OK, these are basically, Bergström defined these identity operators as string layers because they can always read and then eventually may output what was read before. And our usual instance of this ID op is to give the empty buffer as argument, and then you use the letter I as the definition of this operator. So when we see the axioms later, when you see this I, we are talking about this instance of ID op. Okay, the next operator is the composition operator. And this is the type of the composition operator. So what we are doing here, we are composing two operators, as shown by this picture. And as argument, of course, we receive the two operators that we are composing. And now the thing is we need to decide or define how we connect the two operators. And this is given by this function here, which is we call the wiring function, which is a function that maps the outputs of the first operator with the inputs of the second. And as you see here, this is a partial function. I'll talk about more of that later. And the next argument is, of course, a buffer for this operator. And as you see here, the return type is an operator that uses the sum type here, right? So the in-lefts of the sum type are the first operator, and the in-rights are the second operator. Two usual instances that we have for this comp op is the parallel composition. And the parallel composition is basically when we take the constant function that returns none as the wiring. And we have sequential composition, which is when we take the sum constructor as the wiring function. And for sequential composition, we can even map the sum type out from this comp op here, because this is safe to do. OK, so let's define comp op, or this is not exactly the definition of comp op, but is an equation that characterizes comp op. So again, we have a choice, and the choice has a set that we split into parts. The first part are the things that we get from the choices of the first operator. And then we have here a figure to help us understand what is going on. So let's say if the first operator is reading, so we have here, I don't know if you can see, we are talking about this case here, and when you see something green here, is associated with the green part of the code. So if the first operator is reading, all we need to do basically is we need to make the composition read as well. But we need to use the in-left of P because we're talking about the first operator. And then if the first operator is writing, we need to do a case analysis here to see if you're writing to the outside or writing to the connection to the next operator. And if you have none in the wiring, that means you're writing to the outside. And then what we do a write, of course, and we need to use the in-left of P as the port. And of course, you have the proper co-recursion here. But if you have some Q, that means you are writing to the connection to the next operator. And in this case, we need to do a silent step. And of course, we need to update the buffer accordingly before doing the co-recursion. Well, it's actually pretty important to have the silent step here, because later we will want to show some axioms. And for example, associativity of sequential composition would not work without this silent here. So we have tried and we have proved that it does not hold even. And of course, we have this easy case in which the first operator is just doing a silent step, and we just do the silent step of the composition in this case. Now we can look at the second operator. Again, we look at the choices of the second operator. I'll explain the sound reads in a second. So let's see what happens if the second operator is reading. Then we check if you're reading from the wire or not. If you are reading from the wire, that means we need to actually protect the situation in which we are reading from a port in which the buffer is empty. So that's why we have the sounds reads here. So the sounds read is to guard this. So otherwise, we'll have a undefinition in this case. And then, of course, what we do, we give to F the head of the buffer at port P, and we co-recurse with the tail at port P. The next case is when you're reading from the outside, and then it's a bit easier. The only thing you need to do is to use the proper port, the in-right of P here, before doing the co-recursion. And we have not the last case, but another case here, which is when the second operator is writing and is writing outside. And of course, we just need to use in-right of P as the port. And the last case is when the second operator does a silent and then it's just the silent of composition as well. So this is fine. So I showed you 3 operators from the algebra so far, 3 primitives: identity, parallel composition, and sequential composition. We have a few more. So for example, we have feedback loops, and this is the type of this operator. So you see here we also have the sum type, and this M here represents the ports that are looping back. We have the transpose operator that transposes the inputs to the outputs. We have a dumb source operator that is a source operator that never actually outputs anything. So this is basically equivalent to the uncommunicative operators that we saw before. And we have the sync operator that is an operator that can always read, but never outputs anything. And we have the split operator that you read something from one of the ports in N, and no deterministic output to the in left or in right of the port that it read. We have the dual of that, of split, which is the merge operator. So non-deterministically pick the in left or in right, and then output to the port, to the corresponding port. And we also have the copy operator, which is a bit similar to split, but in this case, it will duplicate the element, and it will be allowed to output in both in the in left and in right. And we have the dual of copy, which is a quality test. So you non-deterministic read from the in left and right, and then you enqueue that. And then you basically have 2 queues, and you compare the head of both. If the head of both is equal, you output the sum of that element. Otherwise, you output none. That's why you have the option type here. OK, now we can start talking about the actual algebra, or the properties of the algebra. So let's look at the first few axioms. So there are 52 of them. I'm not talking about every single one of them. That would be too much, of course, but we can look at a few. So D1 here, well, this is basically associativity of parallel composition. Look here, we use map-op to reassociate the map-op because this is necessary. Otherwise, it doesn't type check. We have D3, which is associativity of sequential composition. We have B10, which is something that resembles commutativity of parallel composition, but we need to use transpose here. We have R6 that says that if you have a nested loop, you can represent that as a single loop. And we have the remaining axioms here for the other operators. So A1 is basically a 3-way equality test. That's in this axiom here, like in the left side, we have this 3-way equality test. And the right-hand side, we have a sort of like commutated version of it. A2, we have this new symbol here that is one of elements of this set that has the equality test and the merge. So let's imagine that we take the merge. So this says if you transpose and merge, this is basically equivalent of just doing the merge. A6 is basically the dual of A2. So here we have copy and split as operators. And then we have A11. A11 says if you copy and sequentially compose it with equality test, that is the same thing as just doing identity. And then we have this A10 here. And A10 is a pretty long axiom, as you see. So I will not explain with words. I will explain with a picture. So this is the picture. As you see here, in the left-hand side, we have equality test, sequentially composed with a copy. And the right-hand side here, we have this complicated butterfly-looking picture that uses like identity transpose. And it's pretty complicated to understand what is happening here. But if you play around, you see that this actually makes sense. So, well, how do you prove these two things to be equivalent? Well, you see, of course, you want to use the conduction principle that we have for Wiki by similarity. But we cannot use the empty buffers as instance here. We need to generalize the buffers, right? So that's why we have these unique identifiers there where each buffer will be presented. So we need to, well, now since we have unique identifiers for the buffers, we need to relate the buffers in the left-hand side with the right-hand side. And to make this relation to be sound, we need to find some invariants for those. And I will not explain that here because that would be too much. It's pretty complicated. So you can see the paper to understand details about how to prove this kind of equivalence in more detail. And we also have the things in the artifact too, if you want to go deep in this proof. So I would like to mention some related work to finalize my presentation. So of course, we need to look at Bextra's work. So in that formalization, it's actually just a pen and paper formalization. And they present the operators in a process algebra, where we use Isabelle HOL here. And another important thing is that we actually show the formal proofs, and they don't present proofs in their paper. Another work that we'd like to mention is the choice trees by Chap et al. So choice trees or C trees are an extension of I trees. And of course, they share some similarities of our code data types, meaning they're conductive trees. And they can also represent non-deterministic computations. But one difference is that, well, they are both C trees and I trees are used to represent impure programs in general, where in our work, we are domain specific. We are only talking about, we design an operator that, a code data type that is meant to be used only with non-deterministic asynchronous data flow. And last is the flow language by Laouen et al., which is just a formal representation for different streaming frameworks. So they can represent in the same formal language Flink and timely data flow, for example. Where for us, our language is just Isabelle HOL, and we represent our sim computations using our code data type. Another thing good to mention is the Velos project, which is a verified compiler for the Lust language. And well, this is for synchronous data flow, which is something related but different to asynchronous data flow. So in conclusion, I would like to say that Isabelle HOL has, we could show an instance of non-deterministic asynchronous data flow using Isabelle HOL. And Isabelle HOL has a good tool set for this kind of job. Namely, we have code data types, co-recursion, and conductive predicates. We proved 51 of the 52 axioms. So did we fail to, or we could not prove one of them? Well, we could not prove one of them because one of them is actually false. So we proved that A1 for the merge operator, which is this equivalence here, which is basically like this three-way merge, in which in the right-hand side basically commute one of the merges, right? It does not hold. It is false. And well, it is false. So we showed, we have developed basically 28,000 lines of definitions and proofs in Isabelle HOL, so it was a pretty long development. And well, as future work, we could also show the Brock-Ackermann time anomaly, which is a well-known issue in non-deterministic asynchronous data flow. And since we have submitted the paper, we have developed the basic infrastructure to formalize time data flow algorithms using this as foundation. And now we are working on verifying time data flow algorithms using this as our foundation, basically. So, okay, I think I did on time. Any questions, comments?